Hi, welcome back. Sorry for the technical problems we face here. So we continue now with the celebrations and reflections with Alex Postnikov from MIT. Alex, please, the stage is yours.
So should we start?
Yes, please.
Okay, so, but to start, I need to share my screen. Oh, okay, now I can share my screen. So can you see the screen?
Yes.
Yeah.
Yeah.
Okay, sounds good. So let me start. So, so the title of my talk, so this conference is called Reflections. So I'm going to call my talk Reflections on Cyclicity and Positivity. So the original title announced was Permutohedra and Grasmanian, but I kind of also had this alternative title. So one problem with Zoom talks is that usually in Zoom you cannot scroll back, but actually if you want to scroll back, I put notes like in this PDF file, and there is a link in the chat. So if you open this link in your browser, you can always go back to the beginning of the talk. So if you need. I kind of feel bad because I missed a lot of opportunity. I haven't seen Rona Dean and Yuval Roichman for a while, and I missed opportunities, some opportunities to see them. So for example, this past summer, Yuval was in Boston, but I was actually out of Boston. Then he visited Boston, so I kind of missed him. And I was kind of determined that I will come to Israel this time, but again, because of the known circumstances, I could not come. But anyway, it's better to at least participate remotely. So let me start the talk and let me kind of list some keywords from the works of Rona Dean and Yuval Roichman. So I think the word cyclic is very frequently used in, so I think at least in the last 5 years, most of papers of Yuval had word cyclic in the title. And also some other things that appears in papers of Ron and Yuval is reduced decompositions, true positivity, polytopes. Well, polytopes doesn't appear very frequently in their works, but I counted that at least 2 papers of Rona Dean have word polytopes in the title. And also spanning trees, that's another thing. So, and my initial goal, so I was hoping to kind of tell you how all these keywords also appear in my research, because all these words are very close to my own research. But I think I will not have time to talk about all of them, but I'll at least try to, my goal is to try to explain what's the relationship between the word cyclic and the word positivity, and also word polytopes. So maybe I can tell some personal stories that I met Yuval and Rona actually a long time ago. So then I was a graduate student at MIT. Yuval was a postdoc, and we kind of talked a lot at that time. And then Yuval went to Israel, and he invited me to visit him in Bar-Ilan, and I met Ron. And actually, I've known about Rona Dean even before I known about Yuval. So then I was an undergraduate or maybe even high school student. I was interested in combinatorics, in Kelly theorem, in trees, and I saw papers of Rona Dean about multidimensional trees. So somehow I was interested in this stuff. So anyway, so these are some of the words that they like, and actually I like, and maybe I'll try to explain at least my view on some of these words. The other thing is that to themes in my research, or kind of that appear in my research, is positive Grassmannian and generalized Permutohedra. And originally, kind of these were like just two different subjects, two different topics, and I kind of like both Grassmannian and Permutohedra because they have interesting combinatorial structure. But more recently, I kind of started to realize that there is a close relationship between these two things. So these two things are related to each other much closer than I originally suspected. So maybe I'll try to explain a little bit. Maybe I'll show you some glimpses of this relationship between Permutohedra and Grassmannian. And from a marginal point of view, so Grassmannian is something that lives in the world of algebra, algebraic geometry, and Permutohedra, some polytopes. They live in the polyhedral world. Of course, there are known connections between algebra and combinatorics of polyhedral combinatorics. So, for example, well, very known thing is starting from pioneering the works of Richard Stanley and many other people probably present in the audience is there's a relationship between F vectors and algebraic geometry through toric varieties. So another relationship is between geometry and polytopes is given by tropical geometry. So maybe I'm going to mention some other kind of links within these two worlds. Again, I'm not going to kind of explain everything in details, but maybe just show you some links to kind of, okay. So now I'm going to start with reduced decompositions. Actually, on the right, I'm going to, do you see like these notes on the right, by the way? So on the right, I'm going to like, that's like was kind of stuff that I already covered. So anyway, so reduced decompositions, of course, you know very well that in a symmetric group, any permutation can be written as a product of simple transpositions or adjacent transpositions, and geometrically, these reduced decompositions are expressed by this wiring diagram. So some pictures with wires crossing each other. So in this example, this wiring diagram corresponds to reduced decomposition of the longest element in S4, S2 times S1 times S3 times S2 and so on. And this is called the corresponding reduced world. Okay. Now, I just want to use this opportunity to make a little announcement about this talk that is going to happen tomorrow. So it's a joint work with Christian Gates, Ibogao, Prakavut, Giradilok, and Gleb Nenashev. So the question that we investigate in this work is how many times a given generator can appear in a reduced decomposition. So you fix n and you fix k and you ask how many times, what's the maximum number of times sk can appear in a reduced decomposition. So I'm not going to talk about this question today, but this is a very non-trivial question, and you can, learn about it tomorrow a little bit. And but I just want to kind of mention that the co-authors, Pakavut and Iba, are graduate students who are going to finish MIT soon, so they're on job market. So if you're interested in hiring strong combinatorialists, you can kind of take a notice of these names. Okay, so now if you look at this reduced decomposition here, this picture, you don't see any cyclicity in it. So there are like any cycles, everything is kind of linear. So one question that we're going to answer is, what is the cyclic version or cyclic analog of reduced world or reduced decompositions? So that's, we'll talk a little bit about this kind of. So in general, all objects that will appear today will have some kind of cyclic symmetry. So, but before I do this, let me talk about this usual reduced decompositions. So we can, one thing that we can do with this wiring diagram is to label its regions by subsets of the set of numbers 1 up to n. So here's the example. I think you should be able to figure out how it works. So you label all wires by their left end. This is first wire. And you put label 1 everywhere above this wire. And you do it for any wire. So this way you get labeling of all regions by some subsets of indices from 1 up to n. So we're going to call these collections. And Leclerc and Zelevinsky defined the notion of strongly separated collections of subsets. So a collection of subsets of various cardinality is called strongly separated if for any two subsets, if you take the set theoretical differences, I minus j and j minus 1, then all elements of one of these subsets are less, like any elements of one of these subsets is less than any element of the other these subsets. So this is kind of, the symbol means that any element of this set is less than any element of this set, or the other way around. So this is called strong separation. And Leclerc and Zelevinsky proved that the collections coming from reduced decompositions of the longest element in the symmetric group are exactly maximal by containment strongly separated collections. Okay. So corollary, one corollary of this is that the maximal cardinality of any strongly separated collection is, equals to the number of regions in a reduced, in a wiring diagram, so which is this number. So one question we can ask is, so here in this definition, the subsets can have arbitrary cardinality, but what if we fix their cardinality? What if we fix K and we ask what is the maximal cardinality of a strongly separated collections in this set, n choose K? That's the set of all K element subsets of n. And actually, if you think about this, this question is equivalent to the question that I already mentioned about about multiplicities of a generator in a reduced world. So for example, so let me show you, for example, if K is 2, so we're asking how many of these strongly separated collections have cardinality 2. So it means that how many regions of wiring diagrams are on the second floor. And that's exactly, so in this example, we have 3 regions and there are exactly 2 generators, S2 appears twice. So it's clear that the number of regions here is exactly number of generators Sk plus 1. So this question is actually equivalent to the question about maximal multiplicity. And again, I'm not going to talk about these questions today. But let me mention another definition of Leclerc and Zelevinsky. They also define the notion of weakly separated collection. So a weakly separated collection is a collection such that for any 2 subsets in this collection, and now we assume that all collections have the same cardinality. So for any 2 I and j in this collection, if you take the set theoretical differences and you arrange all indices from 1 up to n on a cycle, and you kind of mark all elements of I minus j and all elements of j minus I, then you can actually find a chord in a cycle that kind of separates one set from the other. So this is called weak separation, and it's a weaker notion than strong separation. So for example, so if you take these 2 sets, 1, 4, 5 and 2, 3, 5, so you take the set theoretical differences, basically remove 5 from both of them. So then one set will be 1, 4 and the other is 2, 3. So then on a cycle, if you arrange indices on a cycle, then they are separated. So they are weakly separated, but they're really not strongly separated. So, and this notion of strong separation is related to the notion of reduced Plagiographs. So let me explain you what reduced Plagiographs graphs are. So by example, so here is an example of a reduced Plagiographs graph. So that's a certain graph drawn inside of a cycle.
Where is the word from? What's the word? Plabic?
Oh, Plabic is abbreviation for planar bicolored. Yeah, so it's planar. These graphs are drawn on the plane and they're bicolored because vertices are colored in blue colors. They're not necessarily bipartite. So in this example, they're bipartite, but in general, we allow edges between two vertices of the same color. Okay, so that's an example of a Plabic graph. And so these Plagiarized graphs will be our cyclic, oops, let me go back, our kind of cyclic version or cyclic analog of reduced decompositions or reduced words in the symmetric group. So this is an example. So vertices are colored in two colors. And there are the following, like, what are these trends? Like in wiring diagrams, there are trends. So what are the trends in these Plagiarized graphs? So there are certain works on these graphs that follow the following rules. So you start at some vertex, and once you see a black vertex, you turn right, kind of go to the rightmost, way to go from this vertex. So, and I forgot to mention that these graphs are planar and they're actually drawn on the plane with a particular embedding inside a disk. And so then you see a white vertex, you turn left. So here is one example. You start here, you turn right, then you turn left, oops, oh, then you turn right, and so on. Oh. My pointer is a little bit strange, but anyway, so you kind of follow this path and you end up in this bounded vertex. So, and there are several conditions on these trends. First of all, these trends should not self-intersect. We don't allow any closed trends, so it's impossible to kind of follow this rule and just come back to the same point. And also, you do allow two strands that have 2 points. We do allow double crossings, but we don't allow bad double crossing. So a bad double crossing is two situation and two strands have 2 common points. They intersect twice, and both of them are directed from one of these points to the other. So like in this example. So this is not allowed. Like all these kind of free situations are allowed. Every graph like this, it comes with what we call strand permutation. Let me show this here. So graph has strand permutation. So basically strand permutation is if we have a strand that starts at ith boundary vertex, it ends at pi sub ith boundary vertex. So then we get some permutation. Okay, so, and let me tell you a version, kind of how to label the regions. Like in case of wiring diagrams, we can also label the regions of these Plagiarized graphs by subsets. So the rules are the following. So you take a graph like this, you take some strand, and you take strand, for example, this one that goes right, left, and it ends at vertex 4. So that's so that means that I'm going to put 4 everywhere to the left of this strand. So every time, so whenever we have a strand that ends at some boundary vertex, I am going to put I in all regions to the left of this strand. And actually, it turns out that in this situation, if you label regions like this, then every region will be labeled by some subsets of the same cardinality. So in this example, this cardinality is k. K equals 2. What we proved with Suhoch and David Spire is that maximal bicontainment weakly separated collections are exactly collections of labels of reduced Plagiarized graphs whose trend permutation had this particular type. It sends I, any index I, to I plus k modulo n, like in this example. In this example, so every index is just has trend starting at some index vertex I, it ends at vertex I plus k modulo n. So, and any such maximal weakly separated collection has the same cardinality, k times n minus k plus 1. So this, in particular, that provides a proof of purity conjecture of Leclerc and Zelevinsky. And I should mention that another proof, like independently around the same time, another proof of this purity conjecture appeared in the work of Danilov, Karzanov, Koshevoy. Okay. So now these are interesting combinatorial objects, but kind of usually, I mean, there are some deeper reasons why people study these objects. So, so let me kind of maybe briefly mention some of these reasons. So the Leclerc and Zelevinsky studied these weakly and strongly separated collections because they were interested in quasi-commuting collections of quantum minors. Well, again, I'm not going to define these, but so this stuff is related to quantum groups. Also, this stuff is closely related to cluster algebras. And also it's related to totally non-negative Grassmannian. So, and there are other kind of reasons, other kind of algebraic reasons why these objects are interesting. So let me talk a little bit about this totally non-negative Grassmannian. So let me remind you that let us fix two indices, k less than or equal to n, then the Grassmannian, and we're going to consider Grassmannian over real numbers. Like one kind of down-to-earth way to define Grassmannian is to think about rectangular matrices k by n of maximal rank and take the quotient of the space of matrices by row operations. So here's some like example of a matrix like this. And now if you have a k element subset of indices, we are going to denote delta sub I, the maximal minor, k by k minor of such matrix. And like in column set I, and of course, so we are looking at minors that lives in all rows and in some kind of columns subset I. So we are taking kind of maximal or some square submatrix in this matrix of maximal size. So this is delta I, and these delta I's are known as Plücker coordinates on the Grassmannian. They form some projective coordinates. And so they're called coordinates, but they're kind of a little bit strange because they're not like the usual coordinates because they're not algebraically independent. There are some algebraic relations between these maximal minors, which are called Plücker relations. So here is an example of a Plücker relation. So for n equals 4 and k is 2, so there is one Plücker relation in the Grassmannian 2, 4, delta 2, 3 times delta 1, 3 times delta 2, 4 equals to delta 1, 2 times delta 3, 4 plus delta 1, 4 times delta 2, 3. And I kind of like to represent this relation by these kind of diagrams. So this product can be represented by these two crossing chords. And there are two ways to uncross these two crossing chords. And they exactly correspond to two terms on the right. And now the totally non-negative Grassmannian is a subset of the real Grassmannian where all Plücker coordinates are non-negative. Now, maybe I should, more rigorously, I should say it because these Plücker coordinates are projective coordinates. They are defined up to rescaling. Maybe I should say they can be made non-negative. You can rescale them to make them all simultaneously non-negative. Okay, so now theorem is that if we have a maximal, so why, like one reasons why these weakly separated collections are interesting. So if you have a maximal weakly separated collection, C of k-element subsets, then the collection of so in other words, collection of labels of reduced plagiographs, then we get an algebraically independent set of Plucker coordinates. Now we actually have a coordinate system on the Grasmanian. There are no any algebraic relations between these minors corresponding to weakly Plucker coordinates corresponding to weakly separated collection. And moreover, any other Plucker coordinate can be expressed in terms of these by subtraction-free Laurent polynomials. So in other words, these weakly separated collections form some nice kind of coordinate systems on the Grassmannian that also have this kind of subtraction-free property. Now, remark is that actually these are not all algebraically independent coordinate systems on the Grassmannian given by subsets of Plucker coordinates. There are others. So for example, if in this example and 4K2, so you have only one Plucker relation. So basically you can drop any of these, there are 6 Plucker coordinates, you can kind of remove any of these six coordinates and you get an algebraically independent collection of Plucker coordinates. But only 2 of them will have this non-negativity property, this Laurent kind of subtraction-free property that anything else is expressed by subtraction-free Laurent polynomial. So for example, if you drop delta 1 free, then you can express this delta 1 free by kind of dividing this Plucker coordinate by delta 2 4. So you get non-negative Laurent polynomial on the right. But if you drop one of these other guys, like 1 2, then you have to kind of move this term to the left-hand side, and then you get minus sign. And these two kind of nice subtraction coordinates that have the subtraction-free property, they correspond to exactly these 2 plagiographs for n equals 4 and k equals 2. So you can check that there are 2 reduced plagiographs in this case, and these are exactly the labels of their regions, and they are exactly 2 weakly separated collections that correspond to these algebraically independent collections of Plucker coordinates with this subtraction-free property. So one question is how to describe all algebraically independent subsets of the Plucker coordinates. So, and in general, this is a hard question. And I'm not going to talk much about this question today, but I want to point out that currently we are working on there is ongoing joint project with these 3 strong graduate students at MIT about low rank matrix completion. And we have some nice results, but there are more conjectures than results. So this is why I'm not going to talk about it today. But I want to mention one case, then this problem is solved. Not by us, but by Daniel Bernstein. Case k equals 2 is solved. And it's already even, this case is pretty kind of non-trivial. So, kind of, there is a solution using tropical geometry. So let me kind of, I kind of do a little bit slow, but anyway. So in this case, if k is 2, then you have a collection of pairs. You can identify this collection of pairs with some subgraph of the complete bipartite graph. So every pair corresponds to h of a graph. So it means that in this case, some subset of Plucker coordinates correspond to a graph. And we want to describe these kind of graphs that correspond to algebraically independent collection of Plucker coordinates. And here's the criterion. Bernstein's criterion is that algebraically independent subsets of Plucker coordinates correspond to graphs that have anacyclic orientations without alternating closed trails. So an alternating closed trail is that a closed walk on the graph with alternating edge directions, but without repeating edges. Now, this criterion is actually a little bit, I mean, it's explicit combinatorial criterion, but it's a little bit tricky because these trails can actually have repeated vertices and not allowed to have repeated edges, but they can have repeated vertices. And if you can unfold this criterion, it's, I mean, it's not totally obvious how to describe or how to construct all these graphs. But for example, reduced Plagiographs, in this case, are in bijection with permutations. With triangulations of the n-gon. So here is a way how to transform a reduced Plagiograph to a triangulation. So, so basically, it's a little bit easier to go from triangulations to a Plagiograph. So you have to kind of draw one black vertex inside of each triangle and make all these white vertices and connect them by edges like this, kind of then erase all blue edges. So anyway, so in this case, reduced Plagiographs or maximum weakly separated collections correspond to edges, sets of edges of triangulations of an n-gon. But there are more, like if Grassmannian satisfies Bernstein's criterion. So any triangulation satisfies this criterion, but there are other examples. For example, here is a couple of other graphs that satisfy this criterion. So for example, so in order to see that they satisfy this criterion, you need to find some acyclic orientation of these graphs. So, so here is like one way to find a acyclic orientation. Again, there might be many acyclic orientations like this. Criterion is that there should be at least one way to direct it such that there is no closed walk with alternating edge directions without repeating edges. Okay. Now, one remark is that, like, for example, in these pictures, in these Grassmannian certified Bernstein's criterion, we don't even label the vertices because any way to label these vertices produce a valid collections of algebraically independent Plucker coordinates. So we can kind of relabel them because this condition is kind of independent on relabeling of the vertices. But if we want to, if we have these positivity conditions, so if we want to have a collection of Plucker coordinates that have this subtraction-free Laurentness property, then actually labeling is going to be important. So for example, so in this case, they correspond to triangulations, and the vertices of these kind of triangulations of n-gon and the vertices of n-gon are labeled by 1, 2, 3, 4 in the clockwise order. So that means that we cannot kind of relabel them in any way, but what we can do, we can cyclically shift the labels. But so kind of instead of an arbitrary permutations, we only allow to use cyclic shifts of permutations. So, and that's kind of one of the instances that I kind of mentioned is that this total positivity is related to cyclicity. So by the way, I have a question. So when I'm supposed to stop? Because I think that originally, I think I was supposed to stop at 7:50 or, oh, anyway, so let me be brief because I think I roughly halfway through my talk, or even less than halfway. But anyway, so let me define another objects. They're called positroids. So positroids are matroids of some special kind. So they correspond to k-element subsets of indices from 1 up to n such that we can actually find a matrix with all non-negative maximal minors such that maximal minor is strictly positive if and only if its index set is in this subset. And it's equal to 0 if this index set is not in this subset M. So they correspond to special class of realizable matroids. And well, I think everybody who worked on the positive Grassmannian knows that one of the kind of crucial property is this kind of cyclic symmetry of the Grassmannian. There is an action of the cyclic group on the positive Grassmannian. So again, if you have this matrix, if you look at the column of this matrix, if you take the first column and move it in the end, and sometimes you have to change its sign, then when you do this transformation, the signs of all maximal minors are preserved. So it induces a well-defined map on the positive Grassmannian, and that explains why the notion of positroids is invariant under cyclic shifts of indices. So if you cyclically shift indices, then positroids remain positroids, but if you permute indices in an arbitrary way, then this positivity property can kind of totally fail. So it means that the notion of positroids kind of naturally comes with this kind of action of the cyclic group. Okay, now let me, since I don't have much time left, maybe let me skip this discussion, but one thing that I want to mention is that all these objects can be understood in terms of convex polytopes. So all these positroids, plagiographs, and so on, they have a kind of natural description in terms of polyhedral geometry. And so, for example, we have a paper with Thomas Lamb, where kind of this called polypositroids, where we kind of discuss this polyhedral approach to totally non-negative Grasmanian, and also its kind of generalization to other Coxeter, like kind of systems. So let me maybe remind you a few things, is that there are some things which are called Metroid Politics. So if you have a Metroid, so if any base of this Metroid, you can associate certain 0-1 vector. So kind of represent every base by a 0-1 vector like this. And then
You've muted yourself for some reason, or it muted you for some reason.
hello, can you hear me now?
Yeah, now the screen's off and I can hear you.
Okay, no, yeah, I had to lay it. Okay, so when did I mute myself? Well, were you like following? Well, anyway, so when should I stop? At like in 5 minutes or now? Or?
PM. You explain what PM is.
Actually, I cannot hear you. What do you say?
You explain what P of M is. You have the time till the hour, so 10, 11 minutes more.
Okay, we have a few more, like 10 more minutes. Okay, and we stop right before convex hull. Okay. Anyway, so for any Metroid, there is something which is called Metroid Polytopes, which is kind of convex hull of these 0-1 vectors corresponding to bases of this Metroid. And there is a famous result of classical result of Gelfand, Gareski, McPherson, Serganova that says that this class of polytopes has a very nice description. So it's exactly all polytopes given by whose vertices are 0-1 vectors, such that every edge of this polytope is parallel to some vector ei minus ej. And maybe you can recognize this as roots of the root system of type A. So we can ask, is there a similar description of...
Small remark. So there is Japanese guy, Tamizawa, who did it 15 years before.
Oh, really? Okay,
yeah.
So maybe this theorem should be...
But it's written in Japanese. The paper is in Japanese, so therefore I learned this from Japanese.
Oh, okay, that's good. Maybe you can send me a reference. Okay, so question is, now we have positroids, which is special class of Metroids. Can we kind of also characterize them in terms of their polytopes? And together with Thomas Lamb, we found such characterization is that, so here are the conditions. We have this condition due to, well, Gelfand, Goreski, McPherson, Sergano, or maybe to Miyazawa. So every H should be parallel to EI minus EJ, but so we have kind of specified directions of edges. Well, we also have some kind of specified directions. So let me show this picture. So we specify direction, but also have some prescribed directions of the normals of facets. So every facet should be given by equation of the following form. We have xi plus 1, and so on, up to xj equals to a constant. And here it's important is that this thing is kind of cyclic intervals. So you have a cyclically consecutive collection of indices on a cycle. So here are a couple of examples. So for example, if you take this octahedron and remove this vertex, then you get this square pyramid, and we created new facet, and it's given by equation x1 plus x2 is 2, and this is a cyclic interval. So this is a positroid. But for example, if you remove this vertex, E13, then you get this square pyramid. So then you get this facet, which is given by equation x1 plus x3, and this is not a cyclic interval. It means that it's not a positroid. And it's also kind of pretty easy to see that this case is kind of, in this case, it's easily to see that these two things, one is the positroid and the other is not, by looking at this Plücker coordinate, Plücker relation. So we cannot, for example, set delta 1,3 to 0 and all other deltas, and make all other deltas strictly positive, because in this case you get 0 in the left-hand side and some positive number on the right. And again, the reason is that this is plus sign. Okay. Okay, now, since I don't have much time left, so let me briefly kind of maybe scan through the rest of my talk. So now all this story, like the other part of the story, I have maybe 5 minutes for the other half of the story, is that there is a nice class of polytopes, which we call generalized Permutohedra. So basically, these are the polytopes which can be obtained from the usual Permutohedron. So that's example of a standard Permutohedron by parallel translations of their facets. So for example, you can start with a hexagon and start moving these facets, but you want to kind of keep all the angles. And sometimes you're allowed to collapse some edge to a vertex. Like in this example, you even can collapse several edges to a vertex, or maybe you can even collapse everything to a single point. So all these are generalized Permutohedra. Okay, and there is a more rigorous description of these generalized Permutohedra. So in particular, this class of polytopes can be described explicitly in this way. We can explicitly describe the inequalities, and the coefficients in these inequalities, like these constants, they are exactly submodular functions. So it means that these generalized Permutohedra are essentially the same thing as polymetroids. Submodular functions and polymetroids are more or less the same things. Now, together with Thomas Lamb, we define polypositroids as the polytopes which are both satisfy, so they are generalized Permutohedra, so they have these prescribed directions of all edges. And also any facet of them is given by equations of this form for some cyclic interval. And maybe to make the long story short is that all nice things that we know about positroids, or most of the nice things, and I didn't tell you about these nice things, but there is a lot of nice combinatorics, it can be generalized to these polypositroids, and kind of the proofs in terms of this convex geometry actually become more transparent.
Just a small question. So your function defined only on subset of 2 power n. So And usual Metroid and Polymetroid is defined on by function f on the, it has to be submodular or supermodular on the 2 in power n on the. So therefore, how it depends on how you extend this function from your particular subset of these cyclic intervals to the whole set.
So there is a way to do it, right? So there is a way to explain. There is like a, and it's not trivial. Like
yeah, so
it's kind of piecewise linear.
It depends on the extension.
There is a way. Maybe I don't have cannot explain you like in 1 minute, but there is a way to do it, and that's a very good question. And it's kind of actually there is some interesting way to expand functions from cyclic intervals to arbitrary subset. But here is like maybe roughly speaking, generalized Permutohedra correspond to submodal functions defined on all subsets, and Polypositroids correspond to submodular functions defined on cyclic intervals. So instead of arbitrary subsets, we're talking about cyclic intervals, and there is a, this is why this cyclic symmetry. And there is a more rigorous way to formulate this theorem. And there are some differences between Positroids and generalized Permutohedra. So one difference is that actually, like any generic generalized Permutohedra, if you don't collapse any edges, then all of them are combinatorial equivalent to the usual Permutohedra. But for Polypositroids, there are several different non-combinatorial equivalent classes of generic Polypositroids. And one of them is the cyclohedron, but there are other types of generic Polypositroids, and but in particular, one thing is that all of them have the same F vector, which is one nice thing, but combinatorial they might be different. And maybe since I'm run out of my time, I didn't tell you how to define what is the polyhedral version of reduced Plagiographs. And let me show you some pictures. So these reduced Plagiographs correspond to pictures like this. So you can, so they are called what we call membranes. So these are certain two-dimensional surfaces embedded in Rn, which are made out of these little triangles. So they're triangulated in triangles. So, and every edge of every triangle is directed as some vector of the form EI minus EJ. And we want to fix the boundary of this surface. It's the boundary loop. And these membranes has to be minimal. So among all membranes, this is the given boundary. And so this basically property of kind of reducedness property is equivalent to minimality of this surface. And we kind of think about this as a discrete version of plateau problem. So there is a famous plateau problem about the existence of a minimal surface with a given boundary. Now we have a similar kind of discrete version. So we fix this kind of piecewise boundary given by vectors of the form EI minus J by the roots. And you want to fill it, this loop, by some two-dimensional surface of minimal possible area. And there is some combinatorial way to find the area of this minimal membrane and so on. And I think I'm ready for my last slide. So it's, well, it's better late than never to congratulate Ron and Yuval with their birthday. So happy birthday. And thank you very much for listening.
Thank you very much, Alex. Let's see first if there are any questions from the audience here.
stop share.
You mentioned before in these example of the cyclohedral, and you mentioned that all the other examples have the same F vector. Do you have some combinatorial characterization of the phase lattices?
So actually, I cannot really understand what you're saying. It's something wrong with the sound.
You mentioned beforehand the cyclohedral as an example, and the other example says the same F vector, and I wondered about if you know, or you can characterize all those.
Sorry, I think that the only thing that I understood from the question is F vector, but I couldn't understand everything else that you said. I think the sound is not very clear.
Okay, let's move to questions from the remote people.
Okay. Okay, I see there is in the chat, there is a question to Gleb about the reference to this. So,
okay, if there are no more questions, let's thank Alex again. We will reconvene at 10 past as the usual schedule with the Rachel Stanley's talk.